She is currently, amongst others, studying two projects that are interesting to us from the perspective of what we do. The first is that she studies nanomaterial protein interactions with a unique method that she's developed, and she's also interested in studying oxygen radical production in response to carbon nanotubes, and the possibility of quantifying that and measuring that in terms of biological outcomes. So welcome.
Thank you.
And look forward to your presentation.
Thank you. Thank you very much for your patience. It's really not a good planner.
No problem.
First, to just introduce myself, I graduated from Iowa State University with my PhD, and then I did a postdoc in Los Alamos National Lab. Now, this is my fourth year in UC Riverside. I'm an analytical chemist, so we do bioseparation and also biosensing. So because we encounter a lot of this with nanomaterial, so we developed this interest in studying its possible toxicity. So my first two entrances that how we can apply. So I should start here.
Where would you like to start, and then I'll move to intro.
Yes.
Okay.
Okay. Thank you. So we want to explore what kind of application we can find of the methods developed in our lab to analyze the interface between nanomaterial and biomolecules. So this slide won't be very interesting to you guys because we're already working in the area. So I'm going to skip that. But one kind of interest we have. So it's not working on there. Okay. Anyway. Okay. So we're interested in the oxidation effect, like oxidative stress introduced by nanomaterial. Especially, we are studying single-wall carbon nanotube right now. So people find actually there are different levels of this type of oxidative stress in cells or even aqueous solutions, but the reports usually are kind of contradictory. Some people report there are not much enhanced levels. Some people reported there are a lot of enhanced stress. So we want to understand the fundamental factor behind that. So we actually started our study in aqueous solution. So we haven't done any cell tests so far. That's what I want to emphasize because that would be quite different from your research. First of all, we studied oxidative stress using an indicator, the fluorescent indicator, which is very sensitive, but unfortunately they are not very selective. So after you find out they could produce fluorescence in the environment, then you still have to go on to identify the specific species that that generate the fluorescence. So the probe we are using right now is this DCFH, the dichlorofluorescein, which is not fluorescent natively, but after it's oxidized, it will change. It will lose one hydrogen and then become fluorescent. The fluorescent molecule, we call it DCF. So it's an indicator for hydrogen peroxide at the presence of peroxidase, and it also can also be oxidized by hydroxyl radical, peroxyl radical, and the reactive nitrogen species. But it's not responsive to this hypochlorous ion and also the hydrogen peroxide by itself, or this superoxide radical. So what we found out is that in the aqueous solution, once we dissolve the carbon nanotube, there we tested 3 different types of carbon nanotube. This one is the modified one, so it's also called the pristine carbon nanotube. And this one is the PEG modified carbon nanotube, and this one is the carboxylated carbon nanotube. We purchased all this from Sigma. So. And then this is the concentration there in our solution. And after you find all these nanotubes can actually oxidize DCFH to a certain level, especially the unmodified one, which is in the blue line, which is indicated by this line, and the carboxylated carbon nanotube is the black gram. So these two can actually, the original BCF concentration here is 1 micromolar. Actually, it can oxidize almost 80% of the BCF we put into the solution and observe fluorescence. So we want to know what kind of oxidation species are behind this oxidation. So first, the first approach we took is to screen different suppressors, because there are certain suppressors that we can use. So for example, if the oxidation was induced by hydroxyl radical, it should be quenched by DMSO, because hydroxyl radical will oxidize DMSO and generate this methyl radical, which will in turn into formaldehyde. And then sodium aniline should suppress the oxidation introduced by singlet oxygen. However, these two did not work in our system, so they did not have any suppression effect in our system. Only the Clorox, vitamin E, and vitamin C, which are considered good suppressors for peroxide radical, can suppress the reaction. So our assumption is that this type of oxidation species has characteristics very close to peroxide radical. At least the oxidation potential is close to peroxide radical. We also try different surface coating, because all these three types of carbon nanotubes, they have one difference, is their surface property. The pristine carbon nanotube has no modification on the surface, and carboxylated carried carboxyl group on the surface after oxidation in acid solution, and the weight percentage of those groups is 3 to 5%. And for the PEG nanotube, actually it carries 38% of the PEG group on the surface. And that particular type of nanotube, we find the lowest level of oxidation of the BCFH. So we think the surface coverage by those functional groups may matter to the oxidative stress. Therefore, we did not covalently coat the surface again, but we just used a surfactant or protein to coat the surface. So SDS can bind to carbon nanotube very easily, which is the surfactant people use to distribute them in aqueous solution, especially for the modified carbon nanotube. In the modified carbon nanotube solution, we have to include 0.05% SDS to reach the solubility we test here, which is 0.01 milligram per milliliter carbon nanotube in the solution. But for the other two types of modified carbon nanotubes, they have higher solubility in aqueous solution, so we did not use any SDS. However, we find out for the PEG, the original oxidation level around here, so it can oxidize certain level of the HGDCF. However, once you mix the PEG nanotube with SDS, then it's coated by SDS. The oxidation effect will drop more than 50%. But we cannot have this kind of effect on the unmodified nanotube because we cannot dissolve without SDS. However, we did a test that increasing the SDS concentration in the solution from 0.002% to 0.001%. And with the increasing SDS solution concentration, we did see the decrease of the oxidation effect. So we know that actually the coating of the SDS will actually suppress this oxidation. Another phenomenon we find out is that if we add BSA will actually, if BSA directly interact with the carbon nanotube, it will suppress the oxidation. However, if the carbon nanotube is coated by SDS, BSA can no longer get onto the surface, and then it won't suppress, it won't have any suppression effect. For example, in the unmodified carbon nanotube, which contains 0.1% SDS, BSA is no longer effective. So the oxidation level will just be the same as just the nanotube itself. So the surface property will affect this kind of oxidation. And what's the final oxidation agent here? We find out it's the oxygen. Because once we increase the oxygen concentration, the oxidation will increase. And once we decrease the oxygen concentration, the reaction will stop. So however, there is still certain level, even though so this is the time that we purge the solution with nitrogen. So even though we purge it for several hours, actually this is only 5 minutes. It will stop. But even after several hours purging, this would not change. Why is that? Actually, right now, our research revealed that there are actually multiple oxidation species in the solution. Very interestingly, the carbon nanotube itself can be an oxidation agent. And then the second one is the oxygen in the atmosphere. And then if you store the nanotube solution, actually we find out if we store the nanotube solution for a long time and also stomachate it constantly, like from time to time, actually will generate hydrogen peroxide in the solution. However, we did not detect this hydrogen peroxide in our previous experiment because we did not add peroxidase. And with hydrogen peroxide only, DCFH did not react with hydrogen peroxide. So we did not detect this species until we added hydrogen peroxidase, horseradish peroxidase in the solution. So let me explain our experimental results in the following slides. How we find out the carbon nanotube itself can be the oxidation agent. We use the IR spectroscopy. So it's the infrared absorption spectroscopy. So because literature pointed out that carbon nanotube actually can oxidize reductant, small reducing agents. And then they observed that kind of oxidation by IR spectroscopy, but they did it in atmosphere. So they contributed all to the reaction catalyzed by carbon nanotube. And then the oxidation agent is oxygen. However, we find out even in argon, so there's no atmosphere and no oxygen supplied, we still find the DCFH being oxidized. And during that 5-minute oxidation, we could see the change in the CNT absorption at 1,000 nanometers. So at this wavelength, particular wavelength, the increase of the absorption in carbon nanotubes means that the carbon nanotube being reduced. So that means it acts as the oxidizing agent. So this phenomenon is more obvious in single one nanotube modified by carboxyl group, because when it's manufactured, the carboxyl group is added by oxidizing the carbon nanotube in strong acid solution. That process actually introduces this, we call it oxidative single one nanotube. So, or single one nanotube in the oxidizing as the oxidizing agent. So once it's, but after 5 minutes, the change in carbon nanotube itself will stop. No longer how long we observe. So the longest we observe is actually 1 hour. But after 10 minutes, there's no change in the carbon nanotube itself. And also without oxygen supply, the oxidation of DCFH also stops after 5 minutes. So this amount of the DCF generated could be from the carbon nanotube itself, and which is the residue of the DCF design in the nitrogen purging solution. But once we stop the argon here and then actually expose the solution into atmosphere, the oxidation will continue. Oxidation of DCFH will continue. So you will see the increase of absorption of DCF continuously, but no change in carbon nanotube anymore, because those carbon nanotube oxidizing species already consumed in argon by DCFH. And then after we put it in atmosphere, the oxidation continues with oxygen. And then we see the generation of DCF increase. So this demonstrated that oxygen is the second oxidizing agent in the solution. We also analysis the oxidation of other small reducing molecules, toluol, and also vitamin C. Because we found these two could suppress the BCF oxidation in the previous experiment. So at first we assumed that the suppression effect is from the competition of oxygen in the solution. Because both of these two are very strong reducing agents. So if they are stronger than DCFH, they will consume the oxygen first, and the DCFH will not get would not contribute the electron to oxygen, so it will not be oxidized. However, we found out vitamin C can be oxidized by the CNT itself. T3 that means it's the carboxylated CNT, but the effect of Trolox on the CNT itself is very small. We also take the absorption spectrum of Trolox, which can indicate its oxidation, because upon oxidation, the maximum absorption of the Trolox will change from 290 to 275. So from that spectrum, we can judge if Trolox being oxidized or not. But by the CNT itself, Trolox would not be oxidized, at least not to the level that we can observe using the spectroscopy method. However, once we add the Trolox to the solution, the oxidation of DCFH will stop right away. So we still haven't figured out why. And similar phenomenon also observed with BSA. So right now we still think Trolox may be absorbed onto the surface much strongly than DCFH. So actually after the absorption, it will suppress the active site on the carbon nanotube surface. So the DCFH will no longer be oxidized. However, we still have not proved that point yet. And then, so this is the some summary of the absorption spectrum of vitamin C and Trolox, which will tell us the oxidation of these two molecules in the solution. Like I mentioned, the Trolox itself is not responsive to carbon nanotube itself. Only it could be oxidized when HRP is added to the solution. So, which means it's what later on we find out is the hydrogen peroxide. So with the CNT itself, it was not oxidized, but it suppressed the oxidation of DCFH right away. And with the addition of the HRP, the Trolox will be oxidized by HRP and the hydrogen peroxide generated by the CNT solution. And for ascorbic acid, which is also called vitamin C, actually it could oxidize by the CNT solution itself. And the addition of HRP did not change the oxidation level too much, but it did enhance the oxidation a little bit. So that's because the ascorbic acid reaction with HRP and hydrogen peroxide is kind of a slow reaction. So its rate constant is 100 times slower than the rate constant of Trolox. So, but vitamin C is definitely a reducing agent for the carbon nanotube itself. So it could be oxidized by the carbon nanotube itself and also by the reaction catalyzed by carbon nanotube. And the oxidizing agent will be oxygen. And after 24 hours oxidation of the BSA and cysteine, we actually find out the thiol group in these two molecules will reduce. However, like I mentioned before, the suppression effect does not match with this kind of oxidation effect. So the suppression is not entirely from competition of oxygen in the solution, because the suppression will happen within 5 minutes or 10 minutes upon mixing, depending on when we check the solution. However, this type of thiol reduction can only be detected after 24 hours oxidation. And if you calculate the total amount of thiol group being oxidized, actually this amount is much smaller than the overall amount of the BCF that can be generated. If we count, actually for BCF oxidation, it consumes one electron. And for the thiol, usually if thiol oxidized to disulfide bond, they also consume 1 electron. So these two is not equivalent. So the suppression effect is not entirely from the competition of oxygen or the oxidizing agent in the solution. So how we find out the generation of hydrogen peroxide is upon the addition of HRP. At first we thought the carbon nanotube actually enhance the activity of HRP, because we see all these more oxidation of DCF after we add the HRP to the solution. So this is the DCF level generated by single wall nanotube itself, and this is the red line that represents the level generated by HRP. However, if we combine these two solutions, we get a much higher level. So at first we assumed it's the interaction between the enzyme and the carbon nanotube. Actually, we did detect absorption of the HRP onto carbon nanotube by circular dichromosome spectrum. However, we also see the hydrogen peroxide itself, the peroxidase, the oxidation status of the peroxidase will change in the solution, which means actually it may not be the activity change induced by interaction with nanomaterial. So it could be just because of the generation of hydrogen peroxide. So we could see it, once we mix it with the carbon nanotube, it changed to compound 1, and then later on it changed, so it shifted from this is the 0, so the HRP resting status. Once we mix it with carbon nanotube, it changed to the red curve, so which represents the compound 1 spectrum. And later on it will change to compound 2, and then eventually it will go back to the native resting state. And we filter the solution, so all the carbon nanotube will be removed, already have been removed in the solution. So this is the filtrated solution, and still this kind of oxidation effect exists. Actually the speed is much faster, so that we no longer detect the compound 1, which is just an intermediate radical. So that means the reaction is much faster than our observation, because the study we just use a regular spectrometer. So the shortest period we can observe is 30 seconds. If the intermediate lifetime does not exceed 30 seconds, we did not detect the compound 1. So we only detect the compound 2. So the filtration experiment demonstrated that it's the hydrogen peroxide generated in the solution that caused the additional oxidation by the addition of HRP. And again, this type of oxidation will completely be suppressed by Tolox. And actually the level is even lower than the level of after we add Tolox into the hydrogen HRP and hydrogen peroxide solution. So the reaction in carbon nanotube after we add Tolox doesn't matter if there's HRP or not. There's totally no oxidation of the DCF exists. And for BSA, the phenomenon is interesting. It depends on how we prepare the solution. If we mix the HRP and carbon nanotube first, and then add the BSA has no effect on the oxidation. However, if we mix the BSA and CNT first, and then add the HRP, the reaction will be suppressed. So right now we still need to investigate how the BSA carry out its effect on the generation of hydrogen peroxide. The same, we still have to figure out how this hydrogen peroxide is generated. From our experience, we feel that it could be from sonication, because the storage of the solution, once we need to test it, we usually sonicate it for half an hour before we mix it with different solutions for test. So, sonication from time to time may also increase the generation of hydrogen peroxide. But still, and the basic reaction could be the reaction between water and oxygen catalyzed by single wall carbon nanotube. But the experimental conditions obviously affect this type of generation. For example, how you add the BSA and how long you carry out the fermentation. Those are still work in progress. So another evidence we found about the generation of hydrogen peroxide is because once we add the catalase to the filtrated solution, this kind of oxidation effect no longer observed. So because catalase can decompose H2O2 in the solution. So which convinced us that it's the H2O2 in the solution caused additional oxidation effect. So here we compare the both filtered like the carbon nanotube solution prepared 3 months ago and the carbon nanotube prepared 2 weeks ago. So the one prepared 3 months ago, even the filtered solution has a higher effect than the solution prepared 2 weeks ago. So this is with the carbon nanotube in presence, and this is without a carbon nanotube in presence. And this is the oxidation of Trolox. So I don't know. This from the same method, we could not detect any much enhancement of the oxidation of Trolox in the carbon nanotube solution itself. However, then we cannot explain why there is such a big difference when the carbon nanotube in presence and when there's no carbon nanotube in the solution. So this is the red line represents the filtered solution, and the blue line represents the carbon nanotube solution. We detect large difference between of the oxidation of Trolox between these two solutions. However, if we mix Trolox with carbon nanotube itself, we did not detect any oxidation of Trolox. So the carbon nanotube presence obviously enhanced the oxidation of Trolox by HRP and hydrogen peroxide. And then if we compare the 3-month-old carbon nanotube solution and the 2-week-old carbon nanotube solution, the 3-month-old has higher oxidation effect than the 2-week-old solution. So to summarize the above results, we find out that the carbon nanotube itself, if in the preparation is being oxidized, it has this kind of carbon nanotube oxidizing agent. And then this carbon nanotube itself, without oxygen, can oxidize the DCFH, and then itself being reduced. And this effect can also happen on vitamin C as well. And the second reaction is that carbon nanotube catalyzes the reaction between oxygen and DCFH. And this is the one we found out before behave like peroxide radical and can be suppressed by vitamin C, Trolox, and BSA, also SDS coating. Also, some people actually attribute this type of reaction. They actually observe the reaction between other small reducing and oxidizing agents. Once they link both agents onto the carbon nanotube, they find out that oxidation between these two can be accelerated. So they contributed this effect to electron tunneling or electron hopping. There's still no conclusion about which is responsible of this kind of oxidation effect. But then, still, we can see carbon nanotube as a catalyst that enhance the oxidation reaction between this oxidizing and reducing agents assault onto the surface. Because the reaction needs to happen very close to the surface so that the electron conduction by the carbon nanotube can work. So the reaction actually could be affected by the coverage of functional group on the surface, or by the coverage of SDS or BSA on the carbon nanotube surface. And then the combined effect, these two, was the one reported in the JACS paper in 2004. And then they measured the oxidation potential of this type of reaction is around 800 millivolts. At that time, they only contributed to the oxygen in the atmosphere. So we actually observe the change in carbon nanotube itself without oxygen. And then we calculated electron equivalent in the carbon nanotube solution. However, what we got is only 0.03 electron per 100 carbon atoms. That could be due to the difference between the carbon nanotubes we use. They use the hip coat tube, and ours is not the hip coat generation. So the last one would be the generation of hydrogen peroxide. So it could be during storage or sonication, anyway, it's over time accumulation of H2O2. And right now we quantify it, it's around 10 micromolar in the solution was prepared, which is 0.01 milligram per milliliter. This 10 micromolar in the newly prepared, or actually the 2 weeks old solution. And then in the old solution, which is 3 months old, it's about 35 micromolar. So actually, after we quantify this, we know that the previous HRP we put in the solution may not be sufficient. We only put 2 units per milliliter of HRP. And if it's indeed 10 micromolar of the hydrogen peroxide generated in the solution already exists in the solution, so the HRP we added should be much more than what we added before. That's why actually we observe the oxidation effect of DCF actually is lower than if you increase the HRP concentration in the solution. So it actually has very high, I did not put that data up here, but just explain it verbally. Probably I did it very badly. But just my conclusion is that there were very high concentration of hydrogen peroxide generated in the solution over storage. So so another area we work on this related to nanotoxicity is to study the nanomaterial and protein interaction. So we have several separation techniques in our lab. One is capillary electrophoresis, and the other is flow fractionation. For the capillary electrophoresis, we already applied it in the previous research on the carbon nanotube generation oxidation factor. Actually, if we use the fluorescence indicator, CE can be a very sensitive method and also can enhance the specificity. For example, if you are not familiar with CE, it's just like gel electrophoresis, but just we do it in capillary. So the separation efficiency will be much higher. So the sensitivity in detection of fluorescence in CE is about 1 picomolar, but the plate reader we tested is only 1 nanomolar. And we also can separate multiple indicators to enhance the specificity. And another advantage CE has is the low sample consumption. So for example, in the plate reader, we actually can observe the fluorescence of DCF could be quenched by carbon nanotube. So this quenching also observed by other groups with other type of fluorophore, for example, fluorescein. So this is attributed to the peptide stacking of the fluorophore and the carbon nanotube itself. So when we use the microticker plate reader to do the measurement, we have to do the calibration curve every time to adjust this type of quenching effect. But with the capillary electrophoresis, the response is linear because we could separate the small molecule from the carbon nanotube easily. So once it's separated from the carbon nanotube, the fluorescence is no longer being quenched. So this is the electrogram we obtained to show the oxidation of DCFH by carbon nanotube solution. And then here is the experiment we did by adding multiple dyes to confirm it's something related to similar to peroxide radical, because we make the DCFH, APF, and modified dye. Modified dye responsible for actually can respond to peroxide radical, and APF responds to hydroxyl radical, and also other type of oxidative species. And because they respond to different species, and also people have found out they are not responsible for several other things. So if you mix these different dyes together, you can increase your specificity, like by comparing which dye they could oxidize. So for example, if we, in this 3-die system, we find out only DCFH and the basaltic dye could be oxidized. That's why we got the conclusion is something close to peroxide radical. And APS could not be oxidized in the system. And also we mix more dyes in the and test in our solution, in our system. We could actually also include hydroxidine, so which oxidation of which could generate this acetylene anion, so that we could separate the acetylene basaltic, the DCF, and the fluorescein, which is the product from APS. So basically, we have 5 different dyes in our system, and then we can observe the individual change in the solution. So next, we want to apply this type of multiple dye system to screen for other nanomaterial in aqueous solution to see if they could generate any oxidation species. So CE can also be used to study protein interaction with nanotubes and also other types of nanoparticles. For example, we use it to measure the affinity between nanoparticle and protein. So this is just an analysis algorithm. So we based on length-mu isotherm, absorption isotherm. So from this length-mu isotherm, we can actually measure the Kd value based on the change of the nanoparticle bound to protein or the initial concentration of nanoparticle. Or just some compatibility. But here we could measure the mobility change if the binding kinetics is faster than our separation speed. So you no longer observe a separated peaks like in the situation of slow kinetics. In the fast kinetics situation, you only observe the mobility change when you increase the protein concentration. But from that change, we can also estimate the Kd value. For example, this is one example of the slow binding kinetics. So we could observe the 3 nanoparticle peak, 3 protein peak, and the bound peak. So from the area ratio between the 3 particle peak and the bound particle peak, we can estimate the Kd between this beta Kc and the 8 nanometer iron oxide nanoparticle is around 1.2 micromolar. So which is actually kind of high. It's in the micromolar range. Yes, this is one example of fast binding kinetics. So what you observe is the peak mobility change. And then you also use the curve fitting to calculate the Kd value. And here is again in the micromolar range. This is the beta Kc with the 7 nanometer iron oxide. The size difference between these 2 iron oxides is not that much different, so the Kd value is also close. However, if we use another approach to analyze the data, we could actually obtain 2 stoichiometry. And this n will change with protein concentration. So when protein concentration is low, the n number is smaller. And when the protein concentration is high, then the n number would be larger. So which is representative of the non-specific binding. Or also, this n number are larger than 1. So it's also a cooperative binding mode between the protein and the nanoparticle. So we tested 4 different types, including the 8 and 7 nanometer iron oxide nanoparticle and the 10 and 5 nanometer gold nanoparticle. And the the Kd value actually falls beyond the micromolar range. So the largest Kd value is 1 micromolar, and the 7 close to 8 micromolar between the iron oxide nanoparticle and BSA or beta Kc. The gold nanoparticle has higher, smaller Kd, that means stronger binding affinity. So smaller the particle is, the faster its binding kinetics, and also between gold nanoparticles. Smaller gold nanoparticles will give stronger affinity to the protein. Even though all this binding are just non-specific binding, the surface of the nanoparticle only coated by the modification functional group. For the iron oxide nanoparticle is coated by polyacrylic acid, so which carry the carboxyl group, and the gold nanoparticle is coated by the citrate. So there's no modification, other modification on the surface. Another separation technique can help with this type of investigation is this flow field fluorofractionation. This type of separation technique can deal with analyze ranging from 10 micron to 10 nanometer. So it has a very large size analysis range. So we could use this actually to purify the proteins down to the nanoparticle. So the purification of this technique actually is superior to centrifugation and magnetic cool down. So here's one example I put down. So if we conjugate IgG onto this 5 micron magnetic particle and then do magnetic cool down or centrifugation-based purification, like continuous wash. After 6 washing cycles, you still find a lot of non-specific proteins in the background. And this purification is for the complex between protein A and mouse IgG, which this complex can bind to the surface of this 5 micron magnetic particle because the IgG is human IgG is coupled onto the surface of this 5 micron magnetic particle. So that human IgG captures this protein complex, and this interaction happens in the yeast total cell lysate, which gives this big background, severe background, if the washing is not thorough. However, one injection in the flow system will clean up most of the non-specific protein, and then the specific protein will show up very clearly on the gel. So therefore, we can actually apply this technique to analyze what plasma protein can bind to the nanoparticle very strongly. So we incubate the nanoparticle with plasma proteins for 4 hours, and then we inject the nanoparticle incubation solution into the flow system, and then you could see a very big injection peak at the beginning, which represents the free proteins. And here is the nanoparticle fraction. And now we collect this fraction and analyze the protein co-isolated with this nanoparticle. And those could be the protein bind very strongly. However, this one is 6 nanometer, so the separation here is still not fully optimized. You could still see that it might co-eluted with very large proteins in this range. However, if you change the size of the nanoparticle, for example, beyond 10 nanometers, so the separation could be much better. So that we hope we can entirely resolve the nanoparticle and the free protein, so that when we collect the nanoparticle, we only collect the protein that bound to its surface, but not the free protein that co-eluded with it. So anyway, when we analyze the gel, we find much less protein, much fewer proteins on the preparation with the flow. And since these high molecular weight bands are there, so we will say that those could be the co-eluted proteins. One way to discriminate that is that we can inject the plasma protein only into the system, and then analyze it and collect it and analyze on the gel and see if the same bands will show up. But those research is still ongoing in our group. So, at last I want to summarize that we will continue to study the oxidation potential, and also we are interested in different type of carbon nanotube, because so far we only study single wall. How about multi-wall, double wall, and also other type like graphene, other type of carbon-based nanomaterial. What physical property of those materials will change their oxidation potential. And also we would like to apply to the multiple dye system to screen the different blocks generated by these other types of nanomaterial in aqueous solution. And also, we want to continue the method development to identify proteins co-isolated with the nanomaterial is reintegrated with plasma proteins. So those results are all obtained by my group members. We work very hard, and also we obtain our nanoparticles from collaborator Dr. Zhong, who is also assistant professor in our department. And thank you all for your attention.
Thank you very much. We have about 10 minutes for questions. I'm gonna quickly tell you that what you presented is of potential interest to us because oxygen radical generation by nanomaterials is one of the injury paradigms that we're very interested in. And we think that the paradigm of oxygen radical generation is intrinsic to some materials, as well as at the Nano-Bio interface for other materials. I.e., some materials may lead to oxidant injury without the material necessarily being capable of generating oxygen radicals, but in a cellular environment, it could injure the cell to make oxygen radicals. So discerning between material intrinsic RAS production and biological RAS production, we think is important principle. The second is that we're involved in, so you will be talking afterwards to the people who is working on the oxygen radical generation in our cellular biochemistry. And the other side that we're very interested in is protein, is the effects of protein on dispersal of nanomaterials, because we do a lot of our work on the biology of nanomaterials with attempts to get the particles size as small as possible in order to go close to the nanoscale. So I guess you will also sit in, so Ivy can, it's a very short time that we have, but Ivy has interesting results with respect to DSC as compared to serum as dispersal agent, so that's of interest for us to know. So I have a quick question then to ask, is with respect to the carbon nanotube, the single-wall carbon nanotube, when you show us the production of the oxygen radical and where you link that, in some cases, to the carbon nanotube itself, for the pristine carbon nanotube, do you discern between the carbon backbone producing the oxygen radicals as compared to the metal contaminants, the yttrium and the nickel nanoparticles that are often contained in that? Or do you just denote that it somehow is related? Is it the carbon or is it the metal contaminants that's responsible?
We tested the metal contaminant in different carbon nanotube preparations. We tested 3 types, right? All 3 types give us different metal impurities. So I actually have data. I don't know where it, but anyway.
I got the data now, so this clarification.
But right now we haven't, for the carbon nanotube itself, like the IR results show that the pristine carbon nanotube, which has the highest metal impurity, actually do not show that kind of oxidation effect. So by the carbon nanotube itself, and the carboxylated carbon nanotube contains yttrium and nickel. Nickel is about 7 micromolar. So right now we are testing if that 7 micromolar nickel will increase the generation of hydrogen peroxide in the solution. But we haven't concluded yet. And another experiment we need to do to verify the involvement of metal impurity is to clean it up more, to reduce the metal impurity and see if that will reduce oxidation potential. But we actually tested the metal ion itself in the solution, and the metal ion itself did not generate this type of oxidation effect.
Well, so Dr. Wan will show you these data where we have single-wall carbon nanotubes as purified, or pristine as you call it, purified and carboxylated. And we see different cell profiling responses with the as prepared carbon nanotubes being more cytotoxic than the purified and carboxylated, but when we look at induction of cytokine production, the carboxylated is more potent than the pristine carbon nanotubes. And the theories that we need to resolve is it's because the pristine carbon nanotube, because of its metal contaminants, are responsible for increased biological responses as compared to the carboxylated carbon nanotubes, which are more pro-inflammatory. Is that because they're better suspendable? And does that then lead to better cell uptake? So is the outcome the difference between oxidative stress generated in the medium compared to intracellular uptake and processing? So these are key questions that we look to resolve, where some of the technologies that you've shown so nicely here could be of help.
Yeah, that's also one of our interests in solving why the hydrogen peroxide will be generated in the solution. And also it's really indeed the electroconductivity of carbon nanotubes that enhance its catalytic effect between oxygen and reducing agent. So, or it's the metal impurities that play a role here. So those also questions we need to answer.
Sure. So if we take the carbon nanotube and we absorb it prior to Trolox, which is water soluble.
Yeah, vitamin E. Yeah.
Vitamin E. Is that binding interaction a stable interaction? That means if you take that tube afterwards and you put it into tissue culture medium, is it going to still remain quenched?
That's a good question. Yeah, we need to study. Yeah, but we think the special property of Trolox also due to its special solubility. It also has hydrophobic part, right? Even though it has a hydrophilic and it has an aromatic ring. And everything that has an aromatic ring is supposed to have very good pi-pi stacking with the carbon nanotube. That's why we think its interaction with carbon nanotube is much stronger than the vitamin C interaction with carbon nanotube. That's why it could suppress it even largely than the vitamin C, even though vitamin C could be it's one of the reducing agent to carbon nanotube cells.
Also, do you think you were able to take single-wall carbon nanotubes, treat them with Trolox, ionize out the Trolox, and then you'll have a stable coated carbon nanotube that will now have quenched surface effects?
Probably. That's the interesting. Yeah.
Okay. So these are the things that I think you guys can discuss. So I'm meeting with Dr. Zhong at 2 o'clock. So either you guys can remain here and discuss, or you could take it over to the lab. I'll leave that up to you. I think from a practical perspective, we should give you at least an hour. So instead of meeting with you at 2 o'clock, I'll meet with you at 2:15.
Okay.
Is that okay?
Yes. So who will bring me to your office?
Oh, don't worry. We'll arrange for somebody to know.
Okay.
All right.
Okay, thank you.
So you guys decide here, John, you make the call whether you want to just continue discussing here, or whether you want to go over so that we can look at some of that later. But whatever way, you only have an hour.
Yeah.
And I think there's plenty of things that will need us.
Okay. So, do you want to repeat something? Or?
Yes, it's fine.
Upstairs.
Yeah.
Maybe from a or then there. Yeah,
I'm here. I work in Western Africa.
Also the sun now.
I So we are the people working here now.